Okay.
It starts 2 minutes. Why? Yeah, that's good.
So I'm waiting that you give me the start. I mean, Can everybody hear me? Yes, I think so. Probably. Okay. Good. Or not. Whoa. Okay.
Okay, let's start the next session. It's it's about design and analysis of tweakable block ciphers, but mainly about Karma. And it includes two talks. The first one is the Karma V2 family of tweakable block ciphers by Roberto Avanci, Supadip Panik, Ordun Kuhlman, Maria Alceda, Shibam Ghosh, Marcel Nagla, and Francesco Regazzoni. And talk is by Roberto.
Thank you very much. So one important remark, in a couple of days, these will actually mean Avanzi Roberto Maria, because I'm going to leave the company. So let's talk about the family of tweakable block ciphers Karma version 2. So what is Karma version 2? Well, it's a revision of a cipher I presented of software encryption 7 years ago. So, after 7 years, start to each and have new ideas. And the goals were to improve the security and allow for longer tweaks. And we will see why we wanted to do this. Another interesting thing is that, like the previous version, the cipher is entirely in the public domain with no intellectual property rights exerted on any component of it by any party that worked on the design. Okay, this is all good and nice, but why are we doing this? Why on earth do we do the revision of a cipher? I mean, Karma V1 looks fine. I don't have to go through this list, but there's been quite a bit of cryptanalysis, and so far they haven't broken the cipher. So why should I fix something that is not broken? It's against one of the fundamental laws of our way of work. Well, there is a reason. It's not a whim, or it's not just to get another paper published. During the last 7 years, we achieved a better understanding of how to design block ciphers. There's been tremendous progress, and also the requirements coming from practical applications. And for instance, as we see in a few seconds, longer tweaks will allow us to address more use cases and in fact also have better security, which is a bit contradictory. We will see how we do resolve these things. And also the components have been revised in order to get a higher level of verifiable or security on themselves, I mean. So the cipher, like Karma V1, comes into versions with blocks of 64 and 128 bits. The block size is given. The key has always twice the size or up to twice the size of the block, but the tweaks were before as large as the blocks. Now they are twice as big. The second change here is to have better security bounds. So what we were doing before was with a model where we have times memory greater than 2 to 128 minus some epsilon, or 256 if the key is longer. That has been used in Prince, in Mantis, in Karma V1, and this comes mostly from the fact that these are FX constructions or something similar. But some SDOs prefer to have a different type of definition, like if the memory we can use or the data you can collect is less than 2 to 56 or 2 to 80 or 2 to some any fixed bound, then the time of the attack will have to be 2 to the key size minus epsilon or something. And also Prince V2 follows this idea. So in a sense, a better understandable and better applicable security claim. So what are the security considerations that led to the new design? So if we look at tweakable block ciphers like, say, the AES in XCX construction, or the 128-bit version of Karma V1, they have something in common. Whether you have synthetic or random IVs, they do not work well. You have a collision of the IVs after 2 to 64 messages usually. So you'll have to change the keys. And it is even worse if you have a mode like the GCM or any other type that uses counters built of a, say, 96-bit initialization vector, and then you have another counter that is just 32 bits, because then the collision will happen after 022 to 248. So one solution that has been considered by many is to use also longer blocks, larger blocks. Also, then Bernstein has a very nice peana in favor of this. But a 256-bit wide cipher can behave in a 128-bit one. I mean, one of the purposes of the whole Karma and Mantis and Karma story was to have something that is lightweight. So if you're just using one instance of your cipher, you want it to be small and fast. So making it suddenly twice as wide is not the way to go. But if we have a longer tweak, and it's a real tweak, so you don't have a hash function and then you reduce it to your block size, but it actually creates, let's say with 256 bits, 2 to 256, possibly, permutations for each value of the key, then you solve these problems. So, for instance, if you are going to encrypt the memory on a server, you can then push in the new larger tweak space, 64-bit counters, 64-bit addresses, 64 bits or 128 bits of realm identity. And in some cases, you still have room to spare. And for embedded things, I don't want to pull a Bill Gates here, but I mean, I think that 64-bit blocks and 120-bit keys are probably okay. But the focus here will be the large version. So security. So our model is the following. If you have a tweakable block cipher, ideally, you don't change the key often. So we do not consider related key attacks. If you want, you have to harden the key generation and key setting hardware in a special way, but that will not be on the critical path. The tweak, on the other hand, changes often. So the adversary might be able to control it. So we have to consider related to attacks. So we chose not to consider a tweak key, but the tweak and the key as two separate entities with different security constraints. By the way, this is nothing against the tweak key, which is per se a fantastic framework, but we just have a different approach. We also move from the Even-Mansour construction to an alternating key schedule, which was actually even suggested by Itai Dinur the day more or less Prince was disclosed. Because the security bounds are better and that allows us to use the more normal type of boundaries. But on the other hand, as I said, there is a contradiction here. You have a longer tweak, which means that the adversary can inject more entropy in the cipher. So they can manipulate it more. So that's also one of the reasons we revised, for instance, also the key schedule, but also the tweak schedule, in order to offset this a bit. And that's one of the things that actually we have met. Design. So the overall scheme, as we know, as you can imagine from the previous ciphers, is a reflector construction. There is Enigma-inspired thing in the middle that acts like a mirror, that basically, so you have a function, you have this reflector, and then you have the inverse function. The function is essentially just a little iterative block cipher itself. So you have R, little r, many, big R. I hate this thing, but I'm at fault myself. I can't pronounce the R correctly, I'm putting a lot of R's. And on the back side, you have the inverse function. You also have, let's say, AES-ish, just a key addition with an S-box layer at the sides. So it's like two micro AESs with a mirror in the middle. This allows us to use the same circuit for both encryption and decryption with just a minor setup. So what are the building blocks? So the state, well, we have seen that I think at least 4 times during the conference so far, is a 4x4 matrix of cells, which are 4 bits. And here lies a big difference between Karma v1 and Karma v2. Karma v1 created the 128-bit version by using 8-bit cells. In this case, we do something different. Instead of having 8-bit cells, we keep 4-bit cells, but we have 2 of these matrices as 2 layers. So it becomes a tensor, a 3D thing. And the round function, of course, then will have to do something. Otherwise, you're, well, you have the perfect venue for attacks because you would have two independent ciphers. So what we have is that the first operation in a full round is the tweak key addition. So we have the tweak key, round key, round constant, shuffle, tau, is the Midori shuffle, just permutes the cells. You have a mixed column-like operation. You have the layer of S boxes, and you have exchange rows. So every other round, in the 128-bit version of the cipher, the first 8 cells of one layer are exchanged with the other 8 cells, with the same 8 cells of the other layer. And then you continue. And this will allow you full diffusion in 4 rounds instead of 3, since you have very light rounds and you have many of them. At the end, it works. And the reflector here is extremely similar to the one in Karma V1, except that to increase some kind of the symmetry, we have a permutation matrix and reverse permutation, and we have 2 round keys added on the side. It actually makes a few things easier. There's no need to read this slide aloud. So this is just the Midori state shuffle, and that's the one that we used. An interesting observation, it's one of the reasons I love this operation, is that it's basically the square root of the transpose. So if applied twice, you get the transpose of the matrix with some rows and columns a bit modified, but in a trivial way. It's a really funky thing, and it will be useful later. The diffusion matrix is very similar to the ones that I was describing 7 years ago in Tokyo. So we basically use the operation that is just the cyclic rotation, cyclic shift to the left of the 4 bits in a cell. Now, this is some nice properties because it doesn't have any XOR anything, so it has depth more or less 0. It is linear, and the 4th operation is the identity. Of course, you will immediately see, oh, we are in characteristic 2, x to the 4 plus 1 is not irreducible. Yes, we are no longer computing in a field, we are in a ring. So in the previous paper, I classified the matrices that were, at least according to my criteria, I'm not saying they are the right ones, but at least the ones that I set for myself, that were good. And the one that we use here has rotations of 1, 2, and 3 places in the first row. It involves only 3 cells. It's involuntary. It's almost MDS. And Karma V1 was using a different one. And that one was chosen over this one, even though it had some slightly worse cell counts, if you look at the characteristics, because it avoided a copy and pasting of characteristics from one cell to the other, a bit better than this one. So for this one, we had to do some extra work. And in fact, it comes from the S box. So there is one person that we all know and love that always found something wrong in what other people are doing. The name of this guy is Tim Bain. And he immediately noticed, oh, Roberto, if you're using the new matrix with your old S box, then there is an iterative invariant of your round function. It probably doesn't break the cipher, but you know, I wouldn't use it. So I had to go back to the drawing board with my colleagues and find a better S box, which allowed us to understand a lot of things. So in fact, with the new S box, we can actually improve, get the better of the 2 worlds. We have a better matrix for considering things also like truncated differentials, or we would have it, but we didn't do this for this paper, and also a better differential behavior. The tweak schedule looks horrible here, but if you notice, there is a function phi, which is a permutation of cells. We start with the 2 halves of the cell on the sides, and then we have T1, then we apply phi, then we apply phi again. And on the other side, we do the same. We apply tau, we apply phi, and then we go back until we get to the opposite. So it is still symmetric, but it has one interesting property. Remember, this is a reflection cipher. The first part and the second part invert each other. So if the same pattern of differences in a tweak part is such that it does not play well with one direction. So it plays well with one direction. So you are hoping to find an attack. It plays well in one direction. On the other side, it probably will not play well. And in fact, this intuition will give us good numbers, as we will see. So, but the challenge is to find the suitable file. So let's see how encryption and decryption work. Okay, I still have time, incredible. So this is a reflection cipher. I'm not going to spend much time here. You start with the plain text, you end up with the ciphertext. To invert the cipher, you basically look at the circuit and invert everything. Now, there is no need to go into the details, of course, of all the all the transformations, but this one and this one can be obtained from one from another just by setting up a few registers in a different way. So you have a wrapper with just one bit. It will set up some registers. The registers are those for these two round keys, these two round keys, these two round keys, and of course, those of the tweaks. But these will set up 7 registers, and it is all fine. Everything else will be done by a common circuit. So there is no need to go into details. You just see the paper. If you have seen reflection ciphers, you know, it's just a bit more cumbersome here. Security. Security is achieved by performing cryptanalysis. So without going too much again in details, because I mean, you can't do much in 17 minutes. Well, 15 actually, a bit faster than I thought. So you have the parameter R, the rounds are 2R plus 2. So, R6 equals to 14 rounds, 7 is 16 rounds. And the numbers in brackets here are the parameters that I had for Karma V1. So what you see, there is no thing such a free lunch. The 64-bit version of the cipher had very tight margins. For the 128-bit version, it wasn't. So what you see here is that using a sandwich boomerang attack, you can increase what you can attack with respect to Karma V1 by a value to the parameter, which is 4 rounds. Everything else is increased usually by 1, so 2 rounds. So with the very large margins of the 128-bit version, we didn't think of increasing the parameter a lot. In 1 minute, I went from 5 to 2. Okay, so there are some parameter choices, so I can skip them. How to find better key schedules. That's the fun thing. F maps one box to one box. So we look at what the difference induced by something here after 2 rounds, because remember, you add the thing derived from the same trick half after 2 rounds. So if we map the cell 0 to cell 0, there is no cancellation. We actually increased by 1 the number of cells activated. But what happens? So we have more choices. But if you look at the other ones, there might be a cancellation, which is actually quite likely because the values are directly derived from the ones we had before. So the problem here is that you have to avoid in any trick shuffle these values. Long story short, it turns out that actually the transpose is the good starting point. Because you see, if you see the 4 cells in the same row, their actions never touch the first column. So what we do, we start with the transpose, and then we start shuffling things inside a column in order to increase the order of these to avoid iterative things. Okay, and that works. So if you look, that was Karma V1, and that's Karma V2 with a tweak that is twice as long. Look at the number of active cells. This applies to both linear and related to the differential. Let's consider related to the differential. As soon as you have a reasonable number, you basically get the same numbers. That also means that the work done before by Byerle and the other Skinny / Mantis folks in trying to find in a more randomish way the shuffle for Karma V1, because it is the one for Mantis that I just stole, well, is nearly optimal. At least I couldn't do it significantly better with theory. So, okay, so the final thing is implementation. Of course, this is one of the slides that everybody hates and nobody wants to read. The point here is that consider Karma with similar rounds like 12 year and 12 year, and you will see that will even be sometimes a bit faster or even 5% smaller. So we made the cipher slightly faster, almost no difference, slightly smaller, even though in the 64-bit version, you have to consider one round or two more, unless you are in some very constrained applications where you don't really care whether it is 64 or 60, the exponent of your attack. For 128 bits, it's the same. The cipher has gone on a diet. You see 1,500 here and 1,400 here. That's optimized for latency. It goes, the difference is smaller, but it's there. You also have the area there, it goes down as well. So we're quite happy about this. And so what can I say as my final words? See you at FSE 2031 for the third version of Karma. And because it's 7-year progression. And thank you very much for bearing up with me talking so much.
Thank you for nice presentations. Do we have questions? Okay. So then I will ask a question. But in general, in many low latency applications, we need, as you mentioned, not only encryption, also decryption to be low latency.
Yes.
And in Prince design, they came up with this alpha reflection property,
Yes.
and it is followed in other low latency ciphers. But do you have any idea about any construction other than alpha reflection to build such a construction to provide encryption and decryption with overhead?
Well, I mean, if you have a construction like the AES even with a different key schedule, you know that you can rewrite the core deciphers so that the core actually is the same at the end. So
Yes,
if you have the right
overhead is like twice or
no, but
so
it is because of the key schedule. So I think with a different key schedule should be. I mean, you'd have probably to be a bit more creative in how I choose the components. I'm not saying that you take plain vanilla ESS, no offense by calling plain vanilla, but see the original version, I mean, and I see, but I mean, and of course, I mean, you can have things like Feisler constructions, which of course will also help you get a single circuit for both things with the right setup and gives you more and more freedom in choosing the round function. Can be insane as long as you do that properly.
I see.
Think with a lot of constructions, it boils down at the end how you choose your tweak and key schedules.
I see. Thank you. Any other question? So then we are late by time. We go to the, let's thank Roberto again. So next talk is Cryptanalysis of Karma 2. And it is by Hossein Hadipur and Yusuke Todo. And talk will be presented by Hossein. Sorry.
Hello, everyone. Thanks, Shahram, for introduction. So this is a joint work with Yusuke Todo, and I'm going to present our attack to Karma v2 that just was presented just before my talk. First of all, this attack doesn't threaten the security of Karma v2. It's just like a more accurate analysis of Karma v2. To analyze Karma v2, we thought integral attack might be the most efficient attack on this cipher. So we focused on integral attack on this cipher. To provide integral attack, we first created a tool to search for integral distinguishers for tweakable block ciphers following the Tweaky framework, because the Tweaky schedule for Karma v2, of course, it's not exactly the same as Tweaky framework, but it's very similar. And we can reuse the tool for this cipher. And we combine some techniques for the key recovery of integral attacks, like meet in the middle technique and partial sum technique, to provide a concrete key recovery attack on Karma v2. So let's briefly review the background. Given that the Karma v2 was presented before my talk, I don't go into the detail. I just mentioned that the key schedule, as you can see in this shape, is completely linear. Given the master key k, we divide it into two halves, like k0 and k1, if it is visible. And then we switch between using k0 and k1 in the forward rounds. And for the backward rounds, we use L0 and L1 in every 2 rounds, where L0 and L1 are essentially the same as k0 and k1 up to the linear transformation. And integral attack, we typically append a few rounds after the distinguisher, so we typically deal L0 and L1 in our attack. We don't care about k0 and k1, okay? And something else is that tweak and key are separated, unlike Tweaky framework, right? Tweak schedule and key schedule are like tweak and key are processed separately, as you can see. And the update function for tweak is essentially a simple permutation on the position of tweak cells, right? And this is the security parameters of Karma v2. What is different than other or ordinary block ciphers is the data limit here. The designers limited the data complexity of a valid attack for 64-bit block size to be less than 2 to the power of 56, and the data complexity of a valid attack for Karma v2 128 should be less than 2 to the power of 80. So it limits a lot of distinguishers that we can use for the attack. Like you might have a very good boomerang distinguishers, but the data complexity may go beyond 2 to the power of 80, right? And another thing is the security parameter, which is the key size minus epsilon. The designers suggested to set epsilon to 16 for the standardization process. So keep in mind that we are not allowed to provide an attack with the complexity of 2 to the power of 127. It's not valid, right? Okay, this is a security parameter, and as I mentioned, we thought integral attack is might be the most efficient attack, so we focus on this attack. But if you refer to the design of to the specification of Karma v2, the designers provided an integral distinguisher for 5 rounds of Karma v2 with 64-bit block size. Okay, but why they didn't provide any integral distinguisher for a large block size? Yesterday I talked to one of the co-designers, and he said applying division property or monomial prediction, these bitwise tools that we have to large block size is very challenging. So you might be able to implement the technique for large block size, but it may stuck in running time. It never terminates, right? So we thought it's better maybe to use the link between zero correlation and integral attack to find integral distinguishers, because we have word-oriented tools to efficiently find zero correlation distinguishers for these kind of block ciphers. So we thought it's best maybe to find zero correlation distinguishers which are suitable for integral key recovery, right? And we use this link from Crypto 2015. This link essentially says any zero correlation distinguisher whose input linear masks form a subspace can be converted to integral distinguisher. This is one example that shows how we convert a zero correlation distinguisher to integral distinguisher. This shape on the right represents a 7-round zero correlation distinguisher for Karma v2. The designers counted the number of rounds as the number of S-box layer. So you see 7 S-box layers. So this is a 7-round zero correlation distinguisher. To convert this zero correlation distinguisher, as I presented in my previous talk 2 days ago, we just invert the activeness pattern at the input. As you can see, only 1 byte at the input is white or inactive. So essentially, in the corresponding integral distinguisher, only this byte, this white byte at the input is active, together with 1 cell of tweak. So the data complexity of this integral distinguisher is 2 to the power of 8, right? It's very, very low. This is one example showing how we convert zero correlation distinguisher to integral distinguisher. Okay, it's clear. But how to find zero correlation distinguisher for tweakable block cipher, considering the tweak schedule? This is challenging. If you want to, again, do it with division property or monomial prediction, it's a more challenge, because you need to handle a lot of copies in the tweak schedule. This shape represents the overall view of tweakable block ciphers following the tweak framework. At the bottom, you see the data path, the round function, and the tweak key is XORed with the internal state. And the tweak schedule is composed of Z parallel tweak paths. In each path, we have an update function, including H, which is a permutation on the position of tweak nibbles, together with alpha, which is a linear, like a linear operation like LFSR on each cell. And in task 2019, a group of researchers provided a very nice miss-in-the-middle-like technique to find zero correlation distinguishers for tweakable block ciphers. This theorem is a little complicated, but I explain it with a simple example here. These are two examples, but please focus on the right-hand side shape. It represents a zero correlation distinguisher for Karma V2 again. To find the, according to the theorem, if you have a input and output linear mask such that there exists one cell in the tweak which is active at most Z times, right? Z is the number of parallel path in the tweak, right? For Karma, it's 1, okay? If you have input, output linear mask such that there exists at least one cell in tweak which is active at most one time for all of the linear threads connecting these two, then this input-output linear mask form a zero correlation distinguisher, okay? I repeat it again. If you have an input-output linear mask like this, for which there exists at least one cell in tweak, one position in tweak, which is active at most one time. Look at the cell number F here, the last one. If you follow the path, you will see it's active only after the reflection structure, right? It's only active one time. So it's a zero correlation distinguisher based on this theorem. But how to find this, right? How to find this? Before explaining how to find this, let's take a closer look at the mixed column of Karma V2 because we want to exploit also properties of mixed column of Karma V2 in our integral distinguisher. This matrix represents the mixed column of Karma V2, and you can see that there is a trivial relation between the input column and output column as is represented here. But how this helps us in integral key recovery? If you have a zero-sum property for xi and xj at the input of mixed column, you can essentially transform this zero-sum property to output of mixed column without any diffusion, because it is directly transformed to yi and yj, the same position at the output, not more than two cells, right? The diffusion effect is bypassed. So if you can even save one cell at the end of distinguisher, then you can imagine you can save a lot of cells in key recovery, because in key recovery, it is propagated to a lot of cells after a few rounds. So we essentially bypass the diffusion effect by these properties. And now let me explain our automatic search for ZC distinguishers. As you can see in this slide, we need two balanced cells like xi and xj to use this property, right? We need two balanced cells. So we need a zero correlation distinguisher with two active cells at the output. That's why we first create a CP model to model the propagation of deterministic linear threads forward in the middle. And then we created two CP models, two independent CP models to model the propagation of deterministic linear threads backward. And then we include a few constraints to provide the requirement of that theorem, which says at there should be at least one cell in Twiki, which is active at most one time, right? CSVM are a few constraints that guarantee this condition. As a result, if you put all of these constraints together, any solution of this model is a zero correlation distinguisher with two active output cells, like this. The upper part is as usual, as you can see, but the lower part to represent these two backward linear masks, I use upper triangle and lower triangle. For example, here you can see two active cells at the input, and if you put each of these backward propagation with the upper propagation, you will see that there is at least there is a cell which is active at most one time. So now we have a zero correlation distinguisher with two active cells at the output. We can convert them to integral distinguisher with two balanced cells at the output. And we can exploit the mixed column property, right? Because the output in the output we have two balanced cells. So with that in mind, let me explain our key recovery. In our key recovery, we combine meet in the middle technique and partial sum technique. Essentially, in integral key recovery, assume that you have a zero sum property for Z, which is an intermediate cell in the cipher, and you want to derive the value of Z from the ciphertext side. If you want to do it, assuming that you have n ciphertext, you should guess K1 and K2 and decrypt C to drive Z, right? The complexity of naive approach is n times to the power of K union K2. But we can simply, we can separate this process. We can drive X and Y separately and check the equality, right? It reminds the meet in the middle technique. Do the first process and store it in a memory, and then the second one, and then check the equality, right? The complexity is reduced to this term. Another technique that we use is a partial sum technique that I also presented in my previous talk. So it essentially splits the decryption process into smaller operations, and each required intermediate state is derived step by step, and it is stored, right? The advantage is that the number of data that you should process in each step is reduced. So the time complexity is reduced. This is a basic example of partial sum technique that I also presented, so I skip in this talk. This shape represents our 13-round integral attack on Karma V2. On the right-hand side, we have a distinguisher with two balanced cells, right? And on the left-hand side, we see the two branches of key recovery. We have two balanced cells. We use meet in the middle technique to drive them separately. And for each branch, we use partial sum technique to do the key recovery. But given that you look at L0, the last run, given that this is common between the two branches, we share this guess between the two branches. Essentially, we have an outer loop in which we guess L0 to save memory, because in partial sum in meet in the middle technique, if you remember, we should store here. We should, when we do the first computation, the upper part to derive X, we should store the key candidates in memory, right? The size of memory we require depends on the size of key, right? If we can share part of the common key in our key recovery, we can reduce the memory. So we have an outer loop in which we guess L0, which is common between the two branches. And then we drive two balanced cells separately by partial sum technique. And then we merge the results to derive this balance property provides 4-bit filter, right? Assume that we repeat the procedure inside the loop S times for S different structures. So it provides 4S filter, right? So in the third step of this loop, we merge the results of the two tables to provide to the power of 64 minus 4S candidates for L1, right? And then we do the brute force over the remaining key candidates to derive the key uniquely. The complexity can be computed because of the simplicity of this approach. So you have an outer loop of size 64-bit, and this blue part represents the first it's not represented in this description, but you can imagine when we guess L0, we decrypt all of the ciphertext up to X3, which is represented by this blue part. And then we do the rest by partial sum technique. So this first term, S times to the power of 44, corresponds to the blue part that we need to decrypt all of the ciphertext up to X3. And then the two terms in the middle corresponds to the partial sum technique for each branch. And we have a brute force phase, which is the last term. For 5 structure, we achieve the time complexity of to the power of 110, which satisfies the requirement of the security parameter. And the memory is dominated by the number of plain text that we need, which is to the power of 44, because the data complexity of this distinguisher, as you can see, it has 10 white cells at the input together with one active cell at the tweak. And result, the data complexity of this distinguisher is to the power of 44. And yeah, we come to the end of my talk. I'm just gonna summarize our results. We provided concrete key recovery attacks on 3 main variants of Karma v2. The novelty of our work was essentially providing a tool for finding integral distinguishers for tweakable block ciphers, following the Tweakable frameworks. It can be applied to Karma v2, Craft, Skinny, Montis, and some other ciphers following this structure. And we also, in the key recovery, we also combined the meet in the middle technique and partial sum technique to reduce the memory. During our search, we found 12-round integral distinguisher, but with a data complexity higher than to the power of 80. One open question is that, is there any 12-round integral distinguisher with the complexity less than this? And another future work could be checking whether other cryptanalytic techniques can outperform our attack or not. But one interesting thing about this integral distinguisher is that why I mentioned we believe the integral attack is might be better. If you look at this, like for example, one of these distinguishers, doesn't matter, it's completely independent of the reflection structure, right? Doesn't matter what you use in the reflection structure, it's completely independent of that. Because of this fact, we believed it might be better than other attacks. Thank you for your time. If you have any questions, I will be happy to answer.
Thank you, Hussein, for the talk. Do we have questions? Maybe short ones. Yes.
So yeah, I have a very specific question. I don't hope you remember it. So the base trail used, I want to know the number of active bits in the data path and number of active bits in the tweak path for the base trail that you have used for the key recovery.
Oh, yeah, for the best train. I think I have some backup slides here. Yeah. This is a little small, I think, but maybe this is more visible. Yeah. Essentially, all of the white cells at the input that you see become active in the integral distinguisher together with one of the tweak cells, only one of the tweak cells. So if, let's say there are 10 white cells at the input, you just add one active tweak cells, which will be 11, right?
Oh, okay.
This is the rule that we convert the zero correlation to integral distinguisher.
Okay, okay.
Yeah.
Thank you.
Thank you for your question.
Any other question? Yeah, I will ask one very short one. In your distinguishers, if I understood correctly, combination of number of rounds is kind of balanced over the middle round. Is it by something structural property of the middle round, or you didn't check the other combination of number of rounds?
Thanks for your question. Actually, the concept of reduced round for Karma v2 is a little controversial. It's not unique to because it's a reflector structure. If you want to define the reduced round and this this design, I think it's not unique. One can interpret differently the concept of reduced round, right?
Oh.
So we try to be fair and also take advantage of this permutation, the tweaks in the tweak schedule. Of course we had better distinguishers or longer ones if we interpreted it in a very unfair way, but we try to be fair and compatible with the specification. Yeah. And it's also unbalanced. We use a different number of rounds before and after reflection structure.
Okay.
Thanks for your question.
So any other question, maybe? Then let's thank both the speakers of session again. Our lunch is waiting for us.